Thank you all for having me here. Thanks for the food and the meal. How many of you were here a year and a half ago when I talked? A few of you have seen me before then. Okay. Does anybody here have any kind of geology background?
2 college courses.
That's good though. That's good. Okay. How many of you are nervous about a major earthquake around here? Nobody. You should be. How many of you were here for the Nisqually earthquake in 2001? You remember how that felt? Yeah, that was an amazing experience actually, to see the ground just doing that. I want to talk tonight a bit about the potential for a large earthquake, and a large earthquake I'm talking about is bigger than the Nisqually earthquake. We're talking about 7.0 and better. In particular, the possibility of having earthquakes the size of the Banda Aceh in Indonesia, or the size of the earthquake in Japan a couple of years ago. All right, tonight the way I'm going to do this is I'm going to break this down into 4 parts. I'm going to do a bit of review about plate tectonics. I'm going to talk about the formation of the Cascadia subduction zone and the Great Terrain Wreck. And then I'm going to talk about the earthquake potential that we have for big earthquakes around here. And then I'm going to talk a little bit about tsunamis and about the potential for having tsunamis locally. In terms of plate tectonics, the way geology has evolved in the last 40 years, almost nothing in geology is explainable without plate tectonics. It's an accepted fact, although it still carries the word theory after it. The evidence for plate tectonics is voluminous magnetism or paleomagnetism, corresponding rock strata across oceans, like where South America used to fit into Africa. Fossil evidence, direct measure of plate movement. We can measure the velocity of plates, where they come together. I'll talk about that later. Seismic activity, geophysical evidence in 3-dimensional modeling has gotten to be an amazing thing, mostly driven by oil exploration, but now with a big focus on earthquake prevention and safety, public safety. Earthquake foci, which you'll see a little bit later, and then the fit of continental coasts, like I said, Africa and South America. Okay, these are what we call plates. Plates are the thin skin on top of the convections on top of the mantle, and they can be 2 different types of plates exist. There's continental crust, which has formed from recycling of oceanic crust. When oceanic crust comes up from the mantle, it's very mafic in composition. It's made mostly of iron, magnesium, silicon, a few things like that. It's very heavy, dense. It's like what you see coming up. Please save questions. It's like what you see coming up in the ocean in Hawaii. It's very viscous, okay? When that same rock is subducted under a continental crust, it will differentiate. Different minerals in it will melt at different temperatures, and the lighter minerals, the lighter elements that melt will float above those others, above the heavier elements. So you over the billions of years of the Earth's history, we've created 2 different kinds of crust. We've created continental crust, the lighter stuff like granites and all those kinds of things, and then we still have the dark, or the heavier, darker, more basaltic and mafic things. Okay. Where the plates come together, there are 3 distinct kinds of boundaries: divergent, convergent, and transform. The divergent boundaries are the mid-ocean ridges. They're where the plates are going in different directions, like the mid-Atlantic ridge, where Africa is going to the east, and South America and the North American plate are coming to the west. That's a real typical divergent plate boundary. There are other divergent boundaries all over. Convergent boundaries are the ones that we're concerned about. We live on top of a convergent boundary. That's where the plates are coming together. And that's where you can get one plate going underneath the other one. and where you can get these major mega quakes. Then there's transform boundaries where plates are simply sliding along each other. The San Andreas Fault is probably the best and the most famous example of that. Here's a diagram that kind of shows them in a cartoon form, where you have mid-ocean ridges, rocks, the mid-ocean ridge here where new crust is forming. These are undersea volcanoes. They're thousands of miles long. They're very active, but they don't have a big tectonic signature. There are not a lot of earthquakes around them, just minor earthquakes. There are transform faults that are sliding, where these things are sliding like this alongside each other. The transform faults are necessary because we're in a three-dimensional globe and you have to take up this strain somewhere. Then we have a convergent plate boundary here where like we have off the coast here, in this Juan Fuca area, where we have one plate going underneath us. These would be the volcanoes like Mount St. Helens and Mount Rainier, and so on. That kind of thing is a convergent plate boundary. What I was saying about the oceanic crust being subducted underneath the continental crust here, as it's subducted under there, underneath this overlying plate here, different temperatures, different minerals. These things rise in magma plumes, so you'll get different rocks forming the volcanoes like Mount St. Helens and Mount Rainier than their original source rocks, which were basalts. These rocks will be less mafic and much more full of silicon, the higher silicon, higher potassium, higher sodium, and less iron and nickel and magnesium. The iron, nickel, magnesium tends to stay deeper. Okay, now that we can date plate, we know how fast these plates are moving. We know how fast the ocean floor is spreading, because we can date the rocks. We've developed really good techniques for dating these rocks, radioactive techniques, radioactive techniques, decay of radioactive minerals. And so in a mid-ocean ridge setting, where we now know that the rocks are spreading in two directions, because we have these stripes which are caused by reversals of the magnetic pole of the Earth. When the rocks originally formed, they take on the magnetic signature based on the magnetic pole of the Earth. When there's a magnetic shift of the Earth, which happens periodically, the North Pole becomes the South Pole, and so forth. We can date those rocks, and so then we can track how far out those and the amount of time that it's taken we can date these rocks. We can say, okay, that's 1 million years old, and so it's gone from here to here in 1 million years because it used to be here, and so forth. And so the seafloor is really striped like that when you look at the magnetic signatures of the basalts that are forming the seafloor. Now, the distribution of the major lithospheric plates of the Earth today, this is the way the Earth looks. These are the plate boundaries that we see today, the continents, in their form that they are now. Here's where we are, my little gold star here. This plate here is what we're going to talk about here today, the Juan Fuca plate. The Juan Fuca plate is a remnant of a much larger plate called the Farallon plate. The Farallon plate used to be about half the Pacific Ocean, and it's over the last 100 million years, it's moved into this subduction zone. Much of it's been recycled, but much of it has been stuck on to the continent. Now this is a pretty cool little diagram of it's the same as we just had, okay? Where it's the same showing the plate configuration today, but this is showing the dates of the seafloor. The younger the rocks, the redder, and then as they get progressively more green and more blue, they get older. Out here, they're about 125 million years old, and you can see there, except for over here in the Western Pacific, there are very few old rocks in the seafloor anywhere. You can see the general age of the Atlantic when it opened about 150 million years ago, and so forth. Not 150 million years ago, excuse me, about 100 million years ago. So this is the kind of evidence that really supports plate tectonics. Now, this map shows all of the earthquakes in the world since 1898 of a magnitude 4.0 or greater. I love the way this looked, and it clearly shows where the trenches and the plate boundaries that were shown before. And you can see here where India is crashing into Eurasia, and you can see these big earthquakes that happen up there in the stands and in Iraq and in Iran. You can see here where, the big earthquakes that happened in the Mediterranean. Those are collisional boundaries. These are where you've got Africa crashing into Eurasia or into Europe. But these are the plate boundaries we're concerned with here. This is the Pacific Rim of Fire, the most active tectonic area on the planet by far. So we can conclude from all of this that plate tectonics is real, and that we don't really need to examine it from a theoretical standpoint. I want you to just accept that that's the way it is for the purposes of this discussion. So now let's step back and see how the Western United States and Canada was formed in the last 100 million years. I'm going to talk about the Great Terrain Wreck here. Terrain is a geological term for pieces of crust that are shifted up onto other crust. So it's like stacking cards and thrusting them together. And that's what's happened to form the Western United States. 100 million years ago, this boundary here, which runs right, was the proto boundary of North America, and it runs from basically western Montana down through central Utah, down into Mexico. Everything in the last 100 million years has been added on there. It's all formerly crust, former seafloor. It's had all kinds of erosion, all kinds of other things happen to it. But that's what we're going to talk about here. And the geological term for each of these things is called a terrain. So this is the way the Earth looked 225 million years ago, one great big supercontinent, and then over time it broke up into smaller continents. And this is where we see it today. Okay, 100 million years ago, the Pacific looked like this. These boundaries here were the boundaries of the original supercontinent, the Pangea one in the last slide. The Farallon plate here is the one that is of concern to us, because the Farallon plate is the one that has basically formed the western side of South America and everything that we have over here in the western North America. It's moving at about 1.75 inches per year in that direction. The point is that the subduction zone has always been along this western part of North America, but the way that they show it in this diagram, the line where this Farallon plate actually was hitting North America is clear back in here. All of this was added by the time this disappeared underneath it. Okay. Okay, so as the plate goes underneath, we get the pieces of the plate will break off. Sometimes those pieces of the plate will get sliced in here and added onto the continent. Sometimes those pieces sometimes that might be direct oceanic crust that is thrown on here in Northern California. There's oceanic crust that has been actually flipped upside down. And it looks like, and some of the rocks are actually upper mantle rocks that are accreted onto Northern California. Where we are here in this part of Washington is we have rocks around here that were actually part of back arc basins and part of spreading centers that have been accreted onto where we currently live. So it looks like this. You can see all these little terrains all the way down here in New Mexico, all the way up here, all of Alaska. All of Alaska was accreted onto the North American protocontinent. These rocks here are all in the billion-year-old range. These rocks here are all in the couple 100-million-year-old range. So when the Farallon plate was crashing in here, it would effectively, part of it would dive underneath North America. Sometimes it would break. Sometimes it would ride up on top. Then it would break off again and kind of go back. And sometimes it would break. It was a constant shuffling like that. So it's a long, long history in Western North America of real extreme violence. Real extreme violence. Eventually, though, the Farallon plate was pushed up against North America, and the Pacific plate, which was pushing it, crashed into North America. This is the way it looks today. When the Pacific plate pinched off the Farallon plate, geologists renamed the two pieces that were left, the Cocos plate and the Juan de Fuca plate. So the piece of the Juan de Fuca plate that we have right off our coast is the remnant of the Farallon plate. It's all that's left of it, is that little tiny piece. And in another few million years, it'll all be underneath here and it'll all be gone. If a major number 9 earthquake were to happen on the Cascadia Fault, it's very possible that it could have repercussions all the way as far south as San Francisco, or vice versa. So why all the concern? I picked these two to put up here because I was in both of these earthquakes. Yeah, I was living in California when this one happened. I was in Pasadena. This is in Northridge, just right across the hill. And in 1958, I was in Yellowstone, and we were going to camp at the Hebgen Lake campground that night. But my mother wanted a shower. We'd been camping throughout. We'd been camping, all over Utah and Wyoming on a summer trip, and my mom just felt dirty. So we went to the Yellowstone Lodge instead. And that night, the Hebgen Lake earthquake happened, and everybody in that campground was killed. You can see what happened. The whole side of the mountain came down right over top, right onto the campground, and the lake rose, and it killed everybody in it. So those, So I have a history of being in big earthquakes too. I've been in a bunch of other ones. I just moved here so that we could have one. So the Cascadia, the West Coast fault line that is 9 months pregnant. The last time the Cascadia subduction zone moved in a big way was January 26, 1700. Geologists estimate that it was a magnitude approaching a 9.0. It generated an earthquake tsunami that flooded areas as far away as Japan. They know that very, very accurately because there were missionary priests in Japan at the time when the tsunami hit, and they documented it very carefully. They knew the time of the day that it got there, and they recorded it in their records, and then they put it away. And then recently, much more recently, scientists looking through those records came across these notes and said, wait a minute. And they looked back to see if they could find out if there was an event, and they were able to put these two together, because on this side of the ocean, they had in Oregon and in Washington, they have very good records geologically. They have a forest that's down near Vancouver, a big old growth cedar forest that dropped about 20 feet straight down, and these big trees are sticking out of the ground. There's all kinds of things like that, and they were wondering, well, you know, what caused this? And then they put two and two together anyway, and so they now know that the exact date that this happened, and it's pretty cool. And they know it was a huge earthquake because it generated a tsunami that went clear across the ocean. Now, Chris Goldfinger is a professor at Oregon State University, and he is probably one of the better people, one of the more active geologists who's studying this phenomenon here in the Northwest. He did a study. This study took 4 years, but it was based on 13 years of research. And these are some of his comments and some of the conclusions that he's made. In the last 10,000 years, there have been 19 great big earthquakes in the 8.5 to 9 range. That's similar in size to what happened in Japan. 19 in 10,000 years, that's one every 500 years on average. There have been 22, this is the scarier part to me, there have been 22 other earthquakes that were in the 8.0 range. But the good news is that major earthquakes tend to strike more in the southern end, meaning southern Oregon, every 240 years or so, and it's been longer than that since the last one. So the probability of an earthquake on the southern end of the fault is more than double that on the northern end. We are on the northern end, if that's any comfort. But by the year 2060, if we've not had an earthquake, we will have exceeded 85% of all the known intervals. So something will break. We are definitely due, and we are definitely pregnant. Okay, this is a timeline showing from the last 2,000 years, and it's got up here, you know, the first, what does that say? First wine, that's very important. First wine, Mount Mazama erupts, different things, different historical events on there. But these great big red blobs, those are the number 8.5, number 9 earthquakes. And you can kind of see how regular they are. They're actually very regularly spaced, except here where they went over 1,000 years. The smaller ones are the number 8s. And here we are today. The Juan de Fuca plate is colliding with North America at a rate of, this is supposed to be 1.8 inches per year, 1.7 inches per year. So I did my wrong math. That's why I was asking somebody. It's probably about 1,500 feet. So in the last 10,000 years, the Juan de Fuca plates moved roughly 1,500 feet closer to us. In a lot of jerks and a lot of real trauma. Now, in cross section, the Juan de Fuca plate is diving under the North American plate. There are earthquakes occur in 3 major zones. They occur in the megaquake area out here, which is the shallow area, where you can break this crust and dramatically drop the seafloor at the same time, which causes tsunamis. We have lots of shallow or crustal earthquakes that can cause a lot of damage, especially if you're right over top of them. And then we can get some pretty big earthquakes right down here on the plate boundary. This area down here tends to be very plastic. It's very hot. Granites a lot of rocks are melting down here, but we can still get some pretty good-sized earthquakes down here. The Nisqually Valley earthquake was a deep earthquake down here like that. But notice that this cross-section is in about the last, I think it's since 1980 something, and there's no earthquakes, even small ones, out here in this megaquake area. So that'll tell us something later. Okay. The last big breakout here in this mega area was in 1700. 2001 we had deep earthquake. We've had them in 1949, 1965. They're pretty common down here. 900 AD, 1872, the Seattle Fault ruptured. That was a big earthquake. That's a shallow earthquake. So really we're looking at earthquakes in 3 areas: the crustal earthquakes, the deep earthquakes, and then the subduction zone earthquakes, the ones out here. Now, one thing that's worth noting is that as this plate on this boundary here, it really sort of rolls over like a, in like a cigar, like the head of a cigar shape there, and you'll get a lot of little fractures along here, a lot of little faulting, and there aren't even any, none of that's been moving lately either. What about the potential for a large earthquake elsewhere, like the Seattle Fault? It's been estimated that if the Seattle Fault has broken in recent history, and it was extremely damaging. If a 6.7 magnitude earthquake were to happen on the Seattle Fault today, because the development in Seattle, et cetera, it'll cause 33 billion in damages and could kill 1,600 people. That's not even the megaquake we're talking about. That's just a little 6.7. Nisqually was 6.8, to put it in perspective. This earthquake is probably very, very likely to happen in the next 50 years. That will be that'll be a major event. And I don't think Seattle's anywhere near prepared for that. The Seattle Fault is what we're talking about, and it runs right through downtown. This is this Olympia Fault down here. This is the one that broke in the Nisqually earthquake. The Tacoma Fault, some of these others also have potential to break, but most of them don't have a history of significant damage. This is a plot of the earthquakes, the magnitude 3 earthquakes for the last 20 years. And I think that it's kind of revealing. You can see they're all over the place in western Washington. A lot of them up here in the South Puget Sound area, including the Nisqually earthquake, which is that bigger circle right there. One of the other interesting things here is in the cross section, you can see that there's shallow earthquakes and there's the deeper earthquakes. But out here towards the coast, there's nothing. There were no earthquakes west of that line in the last 20 years that have been bigger than a 3. Now this just shows some of the historic earthquakes and the sizes. 6.8, 2001 Nisqually. It does show that the shallow earthquakes tended to be inland, farther to the west than the deeper earthquakes. These are the ones that are on the plate boundary where it's being subducted, and they tend to be farther west. By the time the plate moves that much farther, that much deeper as it's going to the east, the rocks become too brittle at depth. Too plastic at depth to break. This is just another figure of the same thing, showing the shallow earthquakes and nothing out here I mentioned before. Megaquake area. So is there another explanation for the lack of major movement on the Cascadia Fault out there in the megaquake area? There may be. Back in the 1970s and 80s, a couple of scientists for the U.S. Geological Survey, Yates and others, thought that this might be the result of hyperlubrication. Subduction zone might be so slippery, they thought that the Juan de Fuca plate was just simply sliding under the North American plate, and there wasn't any big friction building up. This shows the area up towards Vancouver Island where there was a pretty significant earthquake recently. I think it was it a 7? It was a pretty big earthquake. Then down here in Northern California, off the coast of Northern California, where they have a lot of earthquakes. But you can see there's very, very little, almost nothing up here on the Juan de Fuca, on the Cascadia, fault, the one where on this subduction zone. Here's this is the trench here, and there's nothing happening here. This is the spreading center, I'm sorry. But nothing's happening out here. It's basically quiet. And so that causes concern. You can see all the shallow earthquakes in here, and the deeper earthquakes here, but out here where you would expect, where the big earthquakes might happen, we've had nothing, not even little ones. Then in 1979, John Adams, who's a New Zealand geologist, and they're very good geologists in New Zealand, from New Zealand, by the way. I've gone to school with several of them. They were going over some data from the National Geodetic Survey, and he found that the highways along Washington and Oregon coasts were actually rising a couple of millimeters per year. His findings held the ominous portent of a line from Tommy Lee Jones' disaster. Guys, why are the roads rising? This new evidence meant that the Juan de Fuca plate was not sliding easily under the North American plate. It meant that the two plates were completely locked. Pressure has been building and building for 311 years. And if you're a geologist, at this point what runs through your mind is holy shit. What that tells us is that we got a problem out here. We don't know where it's going to break, but we know it's going to break. And when it breaks, you don't want to be on the coast. The Seattle City Council this year, in April, Art Frankel from the USGS was talking about, because periodically Seattle goes through these revisions of their earthquake preparedness and their preparations. And one likely change, and their hazards now they're revising their hazard estimate. The previous estimate would contain a 1 in 500 chance of such an earthquake per year. Based on the fact that we now know that these plates are really actually locked solid, they're revising that, and they're talking about a 1 in 300 chance per year of a magnitude 9. Now that's off the coast. That's still, this has nothing to do with the Seattle fault locally, which could break at any time. But so a 1 in 300 chance per year of a magnitude 9 is what Seattle City Council is, or what the City of Seattle is going to prepare for, what they're basing their risk assessment on. The odds of a megaquake, 80% chance off southern Oregon and northern California, would break in the next 50 years. These numbers, I put these up, they're all different because I wanted to show you that different scientists who are working in the field come up with different statistics and different odds. So, it can be as 37%, 10 to 14%, 40, 27. It's kind of all over the place. I happen to like the 1 in 300 per year myself. But that's per year. And this is, you look at it, 37% chance in 50 years. Okay, when this earthquake hits, when this magnitude 9 earthquake hits, and it hits off the coast, you are going to have 15 minutes to get above 50 feet of elevation. 15 minutes. If you live out there in the Aberdeen, if you live out there, ocean shores, you had better have a plan. Don't ask Jesus to save you. Be your own Jesus. I'd like to see something like this for Washington, but I couldn't find anything, so we'll just use Vancouver. Vancouver Island gets hit by tsunamis quite a bit that are generated throughout the Pacific. If a big earthquake were to happen here off of Tofino, the Canadian Geological Survey did a bunch of modeling on it. They figure a magnitude 9 earthquake would generate a 15-meter tsunami very quickly. This is what it would look like in 0 minutes, 30 minutes, and 38 minutes after the earthquake hits off the coast. In 0 minutes, the earthquake happens. 30 minutes, you're starting to get the preliminary edges of rising seawater. So you have, in this case, they gave you a half an hour before it actually hits. 38 minutes, 8 minutes later, the entire city of Tofino here has been essentially wiped out. You can see on this, they've outlined the town limits here, and you can see that all of this is now gone. And it happens very, very quickly. So if you live out there near the coast, or you know people that live out there near the coast, they really need to have a plan. They need to be prepared. So what do the experts say? It's not a matter of if, but when. Brian Atwater. Chris Goldfinger. There's an 80% chance that the southern end of the fault off of Oregon or Northern California will break in the next 50 years and produce a mega quake. So he's talking about 80% chance in the next 50 years. I don't like his number because it scares the shit out of me. Mark Murray. One cannot rule out the possibility the entire zone will break. The shaking will last for over 4 minutes. If you were in the Nisqually and you can imagine that lasting for 4 minutes or 5 minutes, there's not going to be a lot of wooden structures that are going to be undamaged. You do not want to be in a big building, but then you have no choice about where you're going to be when it happens anyway. Okay, the amount of devastation will be unbelievable. People are not ready for this. When is it likely to happen? We don't know. The media likes to put things in bold black and white headlines, but the fact is that geologic and earthquake science has advanced by light years since the last decade, but we still don't know when they're going to happen. Contrary to the Italians who just put some geologists in prison for not predicting an earthquake. The government created a department of prediction. They had an earthquake. Those guys hadn't predicted it. They went to prison. Yeah, that's scary. They charge them with manslaughter. There's no question that the pent-up stress in the Cascadia zone will eventually cause the plates to slip in a cataclysmic way. But there's no way to tell if that will be in our lifetimes or centuries from now. Remember the timeline I showed there are gaps as long as 1,000 years between these megaquakes. But then we're within the window too. The average is 500 years, and some of them have been as close together as 200 years. So it could happen. You'll be on your own. This is an interesting thing I came across about the first responders are victims. Oftentimes they get down there, an earthquake happens, the first responders go screaming down there, and then the tsunami hits, or then the aftershocks hit, and the buildings that were weakened come collapsing down on the first responders. So the civilians are going to be the de facto first responders by the time it all settles out over the first couple of days. So in conclusions, it's not a matter of if, but when. It could be tomorrow morning or another 100 years. I like the 1 in 300 chance per year. When it hits, it's going to shake for a long time, 3 to 5 minutes, and you're going to feel lucky to survive. If you're on the coast, you have 15 minutes to get above 50 feet. How many of you have packs? How many of you carry those packs with you? How many of you have them in their car today? Very good. I do. Okay, my last slide here. What will a 9.0 earthquake look like? If you Google totally psyched for the full RIP 9, Outside Magazine has an online article, and it's about 8 pages. It's long, and it starts off something like it's 4:30 in the afternoon and a 9.0 earthquake hits 50 miles off the coast of southern Oregon. And then it goes into how long you have, what happens, the whole 9 yards. And it's an extremely eye-opening article about how fast things happen, how unprepared people are, number of deaths, first responders, the whole thing. Oops. So anyway, I'm done. Okay. Mafic rocks are rocks that have extremely high concentrations of iron, magnesium, and nickel, cobalt, those kind of very, very heavy elements. They have low amounts of silicon as opposed to the rocks that are on the continents. The rocks are high silicon. on the ocean floors, and they're low silicon. And as the rocks melt, that silica content, the silica is a very low temperature melting element, so it tends to concentrate itself in continental rocks, in rocks that melt and come off early. The percentage of the direct energy that is going to actually make it into Juan Fuca is a very small portion of the entire size of the tsunami. One of the Canadian geologists was talking about the size of the tsunami in Puget Sound if there was a 9.0 earthquake off of Vancouver Island. And he said by the time it gets to the southern Puget Sound, it'll be in millimeters. Because as that wave comes into Puget Sound, it's dragging on every shoreline along the way, and it's flattening out. Farther it comes in, it turns to the right, to come down one of the arms, it's dragging and it's attenuating and it's losing energy all the way down. And by the time it gets down to our end, it's already being sucked back out the other end because the event is over. Okay, so but that's if the earthquake is offshore and if the tsunami is coming from offshore in deep water. If the tsunami, there is the potential for a tsunami, a local tsunami that would occur, for example, if there was a significant earthquake, vertical movement on the Seattle Fault or on the Tacoma Fault. Those are estimated to be in the vicinity of 16 to 20 feet. And they would happen virtually instantly. And they would be still very localized. There's a tsunami map that is put out by the city of Seattle, and it shows their tsunami zone, and it shows where it would go. And basically what they did is they took and they drew the 20-foot contour line around the local area of Seattle, and they said that's where it's going to hit. So that's where you need to prepare. But that's for an earthquake inside the Puget Sound, not outside offshore. Outside offshore is not going to generate a tsunami that's going to have any real effect in the Olympia area, for example, or that's going to be coming from the north into our area. And we've got a lot of ground between us and offshore. So that's a different deal. A lahar is a massive melting of the ice cap. So the only way a lahar is going to happen is if Rainier erupts. But what happens? A lahar is a landslide event that is caused by a volcano that starts to erupt again, like one that's sound asleep but very active, like Mount Rainier. It suddenly wakes up and it starts to erupt, and the ice flash melts essentially, and comes flying down that mountain, and it picks up everything in its path. And a lahar event will run right out through Puyallup and right out to the mouth of to Tacoma. It'll take out everything in that valley, and it could be 100 feet deep. And there's scars on the sides of the valley around there where lahars have been recorded in the past. A lahar is virtually a semi-liquid state of rock and debris and bits of ice and water and everything else. It's basically, you just flash melt everything up there, and down it comes. The scary part for us is the Nisqually, because the Nisqually Glacier is what feeds the Nisqually River. And there's a dam up there called Alder Dam. And you run a lahar down there, and you bust that dam, and it's going to come ripping down the Nisqually River. And I don't know where it's going to go. I mean, it's going to stay probably pretty much in that channel, but that's going to be a really damaging thing for our side, for us, is a lahar coming down the Nisqually. Once you filter out everything between 3 and 4, a lot of these will go away. And then there's a big cluster of 4s and 5s around Mount St. Helens, because it's still active. It's still moving. But don't be concerned about lots and lots of little earthquakes. Those are good. That's releasing strain. It's out here where you're not getting any strain relief. That's the area to watch out there. You know, we hope to see earthquakes out here. Like in here, this is not bad news. That's okay. This is the release of lots of strain down here. It's in these areas like here where you're not getting that strain released. That's where it's building up, because that's going to pop. And when it pops, it's going to be a great big major event. And then for 20 years afterwards, it's going to be vibrating like Mount St. Helens. It still is. It's going to be vibrating with aftershocks. Like they're just continually happening up and down the Japanese coast, you know, all the way from a 7 to a, you know, 2s, 3s, 4s to 7s. And they're multiple ones every day. And there's still aftershocks as a result of that earthquake a year and a half ago. But right now, we're not getting anything here. If this is Vancouver Island, it occurred. These are thrusts where this bunch of rock here is trying to go to this. What these arrows show here is relative movement. These rocks are moving this way. These rocks are moving up. Okay, so they're just like this, and that's called a thrust fault. When you see that kind of thing, and that's where one of those that earthquake in Canada was, the one that was off Vancouver. And in 3 dimensions, that's the same kind of thing that forms the rest of the whole edge of the plate that comes down the west coast of Washington. That's basically what our offshore looks like. So when you activate one of those thrust faults, you've activated it along the entire horizontal distance of it too. No, they're not thrust. No, they're not thrust faults. They're more strike slip faults. Yeah, and they're vertical. I don't even understand these statistics. I think they pull them out. What they do is they look at the historic frequency, and then they make some guesses. We know that we're within. Right now, it's been 311 years since we had a major number 9 megaquake on the Cascadia fault system. We know that we're now within the window of because the closest window that they have in the last 10,000 years was a little over 200 years between megaquakes. The longest stretch of window was about 1,200 years. So we've now crossed over that. We're now in that line. We're now in that window. When it could happen, we don't have any idea. Now, I think that, you know, the way the science is going, eventually they might be able to put some, we know that off the coast of, we know that the Pacific plate is pushing underneath, or rather the Juan Fuca plate is pushing underneath Western Washington. We know that Western Washington roads are rising. We know that this is building up out here and getting ready to pop. There may be some way eventually that they'll be able to start figuring that kind of thing out. But the science isn't there yet. All we know is that it's imminent. And it could happen, you know, we're within that window of time in the next 1,000 years. It's more than likely, based on the historical evidence on that chart, it's more than likely that it's going to happen within the next 100 years. If you look at the frequency of them, here's the biggest gap, but even it has some 8s in there. Okay, these are 9s. If these are 9s and above, you can see they're very regular actually. Here's 1,000 years, and but then we had 2 of them here. So maybe we're not so due. But it has been 311 years. Part of the way they'll know this energy is because they'll be measuring the energy in India from this event. Okay, so they'll see how much energy got to India from this event, how much of it got to South America, how much of it was in South Africa. They'll feel it throughout, the entire globe will resonate from it. So that's how they can then come back and say, this amount of energy came from this, so that's how big it was. So, but in terms of probably where your real question is how far away will we really feel it? You know, if this happens, well, I can tell you this. Good Friday earthquake, 1963, Alaska. I lived in northern Idaho at the time, and I was in 5th grade. And my mother was 2 steps up to go upstairs when that wave hit northern Idaho, and it knocked her around so where she was holding on to the handrail, and she almost went to the bottom of the stairs. So that was 1,500 miles away. It still had enough punch to make her lose her balance. We're only going to be 100 miles. Unless it happens in Southern Oregon somewhere, then we might be, several hundred miles. Let's hope that it happens down there. Studying center, right on this transform fault, all the way down here, and all the way up through here, they've got a really good, tight array of buoys that are monitoring this 24/7, 365. Anything that happens out there in this system, that data is going to all kinds of different people. The USGS. If that earthquake happens, you're not going to need anybody to tell you. Okay, you'll be picking yourself up and you're going, yes, we had an earthquake.
Right, but the warning systems
out there? You can, now, as far as the tsunami warning system, and we did this for my son, for Daniel, because he was, after the earthquake that happened in Japan, my son was in Bellingham at college, and he was concerned that there could be something else happen. And Bellingham has kind of an open little shot down the Juan to Fuca Strait, and he was very paranoid about it. I wasn't particularly paranoid about it, but I said, okay. So we planned out for him to be able to, we planned out a route for him to be able to leave Bellingham and go up, around, and down, and how to get home if a tsunami hit and took out the roads, because I-5 is vulnerable for a tsunami. If something did happen in here, I-5 could get taken out in this area, but Juan to Fuca Straits is quite long, right? But the U.S. Geological Survey has a kind of an app you can put on your phone, and what it will do is it'll tell you when, and you can set it, you can customize it, and it'll tell you when you can customize it down to where every 4.0 earthquake in the world, your phone will go off. Or you can set it at 5, 6, 7, 8. You can set it at 8.0s in the Pacific Ocean. You can customize it any way you want. And so what we did with him is we got that for him, and he customized it so if there was I think he picked 8, he might have picked 7.0 in the Pacific Ocean, it would go off, right? So at night, if there was an earthquake in the Pacific Ocean, his phone would ring, or it would go off with whatever signal it was. He could look and see. So then he would know that he had time then to look and see if there was a tsunami coming. Because from Japan to here, across that ocean takes 9 hours. That's a lot of time. You can get away. We're going to have, if something happens here, we have 15 minutes. But over in Japan, they have 9 hours. Fear is mostly based on the unknown. And the more knowledge you have about your local situation, whether it's the weather or whether it's earthquakes or whatever it is, the more knowledge you have, the less fear you will have, and the more you'll be able to actually prepare for something